and welcome to another data session brought to you by UrBizEdge. And today we're having a very, very, very special guest by the name Samuel Taiwo. I don't know, I call him Taiwo or Samedo. His topic is going to be advanced feature engineering using Python. Also, I'm using this opportunity to announce our partners, MHS Analytics. So this session is brought to you by the sponsorship and partnership between MHS Analytics in Canada. So for some of you that might be in Canada and might be interested in taking data analytics training, that's data analytics for Power BI, for Excel, and also for financial modeling, you can visit MHS Analytics in Canada, and their motto basically is they are empowered, they're committed to giving their client the business intelligent edge using tools they already have, tools like Excel, Power BI, and some other easy tools like Python and SQL, right? And also they offer a variety of training such as big data analytics, Power BI, Python. So you can go on the websites and just type MHS Analytics, mhsanalytics.com, right? And they are filled with so many topics. So for some of you that might be in Canada or somewhere in Toronto or something, just check out MHS Analytics. Okay, so about UrBizEdge, the sponsors and the organizer of this, why registered Excel consulting, financial modeling, business intelligence, data analysis, and also enterprise solution firm in Nigeria. We also specialize in helping companies and high-value professionals be on top of the business data. We're also the developer of some tools which you can also find in the Microsoft Office store, such as the Nigerian Finance Market Analysis tool, which is available on the Microsoft Office store. Also the developer of the Nigerian Stock Analysis dashboard, and so many other tools you can also find in the Microsoft Office store. As you know, we're also a training company. We have branches in Lagos, Abuja, and also in Port Harcourt. So for some of our upcoming training, this is our calendar. So on the 2nd of June, we have an in-depth Excel training, executive dashboard, and business data analysis. On the 2nd of June also, we'll be having big data analysis using Microsoft Power Query, Power Pivot, and also VBA. That's for automation and some other coding part in Excel. We're also going to have an introduction to SQL for data analysis. So that's going to be on the 9th of June. And our special guest, Samuel, is also a machine learning engineer. So Samuel is highly motivated, independent, quick learner with team leadership skill. He's also a machine learning engineer with over 3 years of Python and C++ development with focus on model building and deployment with emphasis in computer vision, recommendation system, and also big data analysis. Worked with diverse technologies such as building asynchronous API, deploy machine learning model on GCP, and also develop computer vision and NLP algorithm with the ability to convert business requirement into actionable plans. So no further ado, I'll stop sharing my screen and hand over the session to Samuel. So Samuel, I'm going backstage right about now. So Samuel, over to you.
All right. Yeah. Good afternoon, everyone. Good morning, and wherever you are. I hope I'm audible enough.
Yes, you're very audible, sir.
Do I need to turn on my camera or not?
It depends on you now. You're doing trainer. Anything you want to do is fine.
Okay. All right. Let me share my screen and we get started. So we are wasting much time. Yeah. So welcome everyone once again. Today we'll be talking about advanced feature engineering in Python. Feature engineering, as we all know, is something really important and is a crucial step in machine learning pipeline. Okay, before I go further, I just want to say that if you have any question along the way, feel free to interrupt while I'm talking so I can just answer along and move on. So that's okay. So yeah. Feature engineering, it's a crucial step in machine learning pipeline, and it involves selecting and creating and transforming features to improve our model. You know, every machine learning model need features to be able to work. We need data features, and your feature has to be good, has to be of good quality, and you know, as I say, garbage in, garbage out. If you have a bad data, you have a bad model. So your data, the data that you have reflects the quality of your model. So that's why feature engineering can be said to be one of the very crucial step in machine learning pipeline. So we say the importance of feature engineering is important because not all features are equally important in or relevant in the model performance, which is very true. you might have 100 features, 200, thousands of features in your data set, and not all of them will give equal weights to the performance and the quality of the model. So now the question is, how do we, how do we tend to reduce this model, these features? How do we enhance these features to better get out the good qualities in them, and how to process them? We say that some features provide useful information while some does not provide information, and we talk about highly correlated features, where highly correlated features we have to deal with them as well. So the goal of feature engineering is to select and create the most relevant and informative features while minimizing redundancy and noise in our model. So I said note here that feature engineering is not a one-size-fits-all process. It requires domain knowledge, creativity, and experimentation. It is an iterative process that involves continuously refining and improving the features using the model until the desired level of accuracy is approved. So we have to continue to reiterate it. Domain knowledge, as I put it in bold here, it's really important. It's really important. Domain knowledge, having the domain knowledge of your data is something that is important, and it's not a one-size-fits-all for which is the feature engineer. So if there's any problem, let me know, and I hope my screen is good enough. So
awesome.
okay, yeah, thank you very much. So for today, we'll be looking into the feature selection techniques, feature creation techniques. We're looking at ways to handle missing data, and we'll be looking at handling outliers. How do we deal with outliers? We see, I've seen common ways that people deal with outliers that are not really on par to getting the best out of your features and getting the best out of the outliers themselves, because outliers are data points as well. And we talk about dimensionality reduction. This is where we'll call it a pause today. So first of all, before we start, I've talked about our data set. Just a simple data set we're using to show us this process that we're using to the techniques that we're using. So it's a simple car data set, and I think it's part of when you download the GitHub, go to GitHub, you can find it in the resources, the data set used. So you can, let me open a new link. It's a Kaggle car data set that you can find on Kaggle. So it has about about, I think, how many features does it have? Yes, sir. This is taking quite too long. Okay, about 16 features with 11,914 data points. So that's all that we have to make: the model, the year, the engine fuel type, the engine HP, the cylinder, category, vehicle size, the style, the highway MPG, the popularity, and the MSRP, which is the manufacturer's suggested retail price, which is what we're trying to predict. So first, we've just built a very, very simple base model to just see what we'll have here. So we look at minimal data analysis. We won't be doing much of data analysis. Our focus here today is just to look at the feature engineering steps that the various different feature engineering steps. And feel free to follow along, please. The GitHub link, I think, has been shared in the chat. And if you have any questions, feel free to post me along the way.
Okay. Samuel, sorry.
Yes.
Very sorry. So
Yeah, no problem.
can you increase the font size a little bit? People are saying they're
All right.
having issues seeing the font size.
How
I'm very
about this
sorry
now?
for interrupting.
Yeah, no problem. How about this now?
Okay, it's okay, my hand. So JSN, Lekki, is okay by you? I think it's okay. You can continue. Yeah, it's fine. It's fine. Thank you. Sorry for
Okay.
interrupting you.
Yeah, no problem. Okay. Yeah. So so a simple function to encode our label. These are just simple things that we can do. Then we removed our target, which is the MSRP, the manufacturer's suggested retail price. We drop it from the main data because we want to perform some data analysis and feature engineering and stuff in there. We encode our categorical columns. Yeah, sorry, I'll be skipping most of this part because it's not like really the main point of it, the lecture. So, and because to cover most of our time. We input our missing data. These are just simple steps because I just want to build a model to do some stuff along the way when we are using when we're doing some feature engineering techniques, and we use simple inputer to input most of our missing data. We have a df.head, so df imputed our imputed data. So from there, we don't have any missing data again. After using the simple imputer, we've checked, verified if there are no simple imputer, and we can see that there are no missing data. We scaled our data because we have large range. We'll talk about scaling when we get down, but I'm scaling because I'm using a random forest model, and I need to train with it. So a normal distribution Gaussian. Sorry, I'm skipping through this part because So build a base model with random forest using an estimator to random state 42, and we predicted and did the root mean squared error, which we have a score of 9,547. So getting to the main part of this lecture, as I have 45 minutes, I have to use my time wisely. So we're looking at feature selection techniques now, right? So we have, as we said earlier, we have hundreds of features, thousands of features. Out of these features, not all of them are really important. None of them are really necessary to build our model. Most of them have high correlation with each other, and we have to like select the important features among those ones. We have to get out the features that we know are relevant, features that are good to to reduce the dimensionality of the data and eliminate irrelevant redundancy. I said a note here that when selecting feature, it is important to keep the end goal in mind and consider the requirements for the model being developed. Which is very important. So irrespective of the techniques we use, irrespective of the pattern or the style we use to select our feature, we have to put in mind that the end goal, which is to build a model to attain so thing. So if you are building a model to as for example, predict the house price now, it is very reasonable for you to put in the streets, the rooms and stuff like that. So even when you're saying you have like 1,000 feature, removing those key features might not make sense because they will not they are key to giving you a better model, quality model, to get you to get quality result from your model. So we'll talk about different techniques that we're going to use today. Univariate feature selection. I'm sorry, let me just put the time beside me. Okay. Okay, yeah. Univariate feature selection technique. So this is one very common selection techniques that involves selecting features based on their statistical significance with the target variable. So we talk about calculating the correlation between each features and looking at how significant they are, calculating looking at a single feature, variable feature with the target, and looking at how well it contributes to the target. So I said the commonly used univariate feature selection technique here is the Pearson correlation T-square, the ANOVA L1 regularization. You have the feature. So did I? Sorry, just I hope I did run this. Okay. Yeah, just okay. So to use for this example, I'll be using the Pearson correlation coefficient, and so to select, we're using sklearn feature selection, which is select k-best, select k-best, and we're using f regression because we are dealing with a regression tax here. And there are other score functions that you can use. This is classification when you're dealing with the classification for using the T-square, using the f regression, select percentile, that is to select feature based on their percentile of y scores. So there are a lot of other scores that you could use down here. You select k-best. So we use select k-best to get the select top 5 features, right? So we're looking at the top 5 features. This is a univariate technique to get the feature based on their individual statistical significance with respect to the target variable now. So we're using the SK select best score function, F regression. We're selecting the top 5 features. Now, remember, we from our data analysis that we so that we have 15 variables, 15 distinct variables. So we so we select feature transform to using the df imputed, that is the data frame that is imputed and clean, and we select the names, get the names of the feature, and when we run that, uh, we get the these are the top features that we get. We get the year, the engine HP, the engine cylinders, the transmission type, and the market category. So even using normal human sense, we'll get to understand that this feature here, this 5 features that we've selected, these are like really important thing when you are looking at the market value of the car, what of the car. You like tend to like, okay, look at what the year is, the engine horsepower. Okay, how many cylinder does he have? Is it V6, is it V8? The transmission type, automatic or manual. So market category. So these are kind of things that are made very important to you when you're selecting a car, and the value that the car is worth. So this is like the top feature. You can decide to select the top 6 features that you decide to select. We have the highway MPG. So depending on how you go with, but understanding that this technique is significant with a target variable. That is, you're just looking at the individual feature significance. Yeah, please. Any question? Just pause me. Feel free to interrupt me. Now, feature importance. We're going to another technique in feature selection, as we said. Feature importance is a technique for feature selection. It involves determining relevant feature based on in a data set using a model. So this is a very, very common approach that is usually used in machine learning today. So you just build a model, usually random forest. You can use any gradient boosting model. And yes, they have this they have this within the model. So as earlier, I used the random forest to build a simple a base model, which is something which I'm doing. This is something I'm doing now. So we have the feature importance and the RF model. The feature importances, you use the feature importances, the variable to the method to get from the RF model to get your feature importance. So putting in a data frame, we have something like this. So the engine HP, the engine cylinder, the city MPG, the model, and the year. So from the model that we built above, the base model that we built above, so these are like the feature importance, the features and their importance score within them. So most gradient boosting models, they have this incorporated within them, that when you're done building the model, you look at the important features that the model used. That is the important features that was used to build the model, that has significance, and that's significant to build the model, and then we can compute them to see, okay, these are the features that are really important in this model. So that's for feature importance. And we're going to talk about correlation matrix now. So correlation matrix is another technique. It's very common. It's widely used, and it's just a simple visualization way to understand feature correlation. So you look at the highly correlated feature that are less correlated. So depending on the way you want to go forward, further down the line, we'll talk about feature interaction. And feature interaction is a way where feature interact together. So you can consider highly correlated features and less correlated features. So depending on how you go with it, but most times it's best to remove highly correlated features that are correlation with each other, just remove them out. So, but here now we're talking about we're using correlation matrix to look at these features, to look at, okay, how do they correlate with each other? And yeah, it's just a simple using as DF imputer, the correlation. We'll do that for plotting a correlation matrix. And yeah, this is just something simple, a correlation matrix telling us. Let me reduce this a little bit to show this for now, and I'll increase it back later. So of course, the make should have a correlation of 1 because it's the same data. When you look at the make and the popularity, the correlation is -3. They're not correlated at all. And you look at set like the 0.7, the engine cylinder and the engine horsepower, which is, yeah, it does make sense for those two data to be correlated because your engine cylinder actually determines your engine horsepower. So the amount of cylinder determines the horsepower. So you look at these features. This is another way to, to select your features, look at your features and understand this feature. Now, yeah, I have to time. Okay. Okay. The last one is recursive feature elimination. Under feature, okay, what's wrong? Okay, sure. Under feature selection, under feature selection technique, the last one is the recursive feature elimination, REF. RFE. This particular method is like a variant, or I would say, yeah, or a subset of a wrapper method. So wrapper method is like, yeah, okay, it's a specific implementation of a wrapper method. So the wrapper method is where you build a model and use the model to select those top features within them. So you build a model using a subset of your data set, and you use that model to select the top features. So you select the top features. Now, using recursive feature elimination is now looking at all these features and recursively eliminating features that are less important, right? So it is, as I said, here is a specific implementation of wrapper method. It start with all features and recursively eliminate the least important features based on their coefficient or importance score. Yeah. So I said RFE provides a feature ranking based on their importance, which can be useful for feature selection. So using the linear regression, a simple model, we just estimated, we set number of features 5, then we feed it to our DF imputed and Y. So recursively, it removes the features that are less important and give us features that are important. So using this gave us engine cylinder, the transmission type, the top 5 again, the driven wheels, then the number of those, the vehicle size. So so one thing that, as we said earlier, it's an iterative process, it's not a one size fits all. So you have to like look at, okay, if I'm using this technique, am I using RFE? Am I using univariate technique? Am I using feature importance? What technique am I using to select these features, to select the important features in my data set? So yeah, so these are the techniques these are the lead techniques that you can use to select features. There are other techniques that, of course, you can check. There's using building machine learning model to select important features and whatnot. So there are other techniques that we can use to select these features. And once again, we have to put in mind that doing this is not just a one-time thing where you do this. You have to continuous implementation and integration of these techniques into building your model. So yeah, closer. Feature creation technique. This is another feature engineering part, which is about creating features from the features that we have. So okay, so when we're talking about feature engineering, we talk about it being creating features and creating important features, selecting important features from our data set. So feature creation is something important in feature engineering as well. I said here that when creating new features, it is important to consider the impact on the model performance and to avoid creating features that are highly correlated or redundant. So this is really important. Features that are highly correlated. We should when we build a model, create features is a reiterative process. Create features, look at how it affects your model, look at how it scores with your model, then remove it if they are redundant or if they are highly correlated with other features that are within your data set. Now, and the fun part, the thing is that we've actually done a feature creation using feature scaling, right? We scaled our data set up here when we're using a simple standard scaler to scale our data set. So I think we have okay. Yeah, and okay. So one of the reasons why we scale is because having different scales can lead to one feature dominating the learning algorithm. So, for example, when in our data set, going back up a little, when we look at the the data set that we have DF imputed without scaling. We look at the popularity, right? When we look at popularity, we can say that the max in popularity is 5,657. That's the max variable there. And compared to transmission, what transmission type where you have just three, driven rules where you have just three, right? So when you're putting all these features, you're just pushing them into a machine learning model without trying to like scale them within a range, putting them within a normal distribution of a mean of 0 and a standard deviation of 1. It tends to like affect the results of a model. Well, some tree-based model, yeah, it has been said that tree-based model are invariant to scaling, so they're not necessarily needed. But what is really important to get your feature to scale your features, and you can use standard scaler. Another method you can use is log transformation that I talked about here. Involves taking the logarithm of your features. It is useful when working with features that are skewed to distribution. Yeah, as you said. So when you have a data set, for example, going back up again, yes, sorry. When you have your data set, using the okay, for example, let's take the DF imputed. Let's work with the DF imputed here. When we work with the DF imputed, and we let's draw the normal distribution, the Gaussian distribution of the data set. We see that it is something around, we see the range of our value. We have minus 500 going from 0 down to 750. We have something like that. But now when we try to use our after scaling, right? When we try to use our scale DF, so when we try to use our scale DF, we see that it has been reduced. The range has now been reduced, which is like something that is really important, because large range of value tends to like give the model tends to take weights from higher value and make them more important than models than variables with data sets with less range between the highest and the lowest variable. So we should put that in. We should understand that. So as I said, considering our data set that includes engine HP popularity, which are in large range and are heavily skewed towards R values, taking the algorithm of the data set can help to reduce the impact of outliers and bring closer to normal distribution, making the data more suitable for use in machine learning model. So yeah, sorry, I'm quite fast because I have to meet up with time. So yeah, once again, any question, please pause me. So using
Okay, there are
NP.
some questions. I don't know if you want to take it now.
Okay, there are some questions. Okay.
Yeah,
okay.
should I read it out for you?
Yeah.
Okay. So Shagun is saying that, is there any disadvantage of using log transformation for feature creation?
Log transformation.
Yeah. For feature creation.
Is there any advantage?
Is there any disadvantage of using log transformation for features creation?
Yeah. Okay. For feature creation now, right? One of the main reasons why we're doing it is just to reduce the range, right? To reduce the range of the data, because one thing is that you have a large range. But for using log transformation, I don't think there is any disadvantage to using it. To using log transformation to create new features from a data set, because one of the things, let's notice that one of the things is that this data set that we are creating with log transformation, we are pushing it into the model, because as I said, dealing with large range of features, when you are dealing with large range of features, they tend to, number one, skew your data set that is not bringing it to a normal distribution, which we can put in that. And number two again is the range of your data set when you are putting the range. So when a particular feature has a very high range compared to another feature, then you have to understand, then you have to take note. Your model will tend to give the feature with higher range a higher width than the feature with lower range. So for example, in our engine cylinder, which the highest you can have probably is 8 or 16, and considering the year probably 2011, 2012, 2013, 2014, you saw something like that. So the ranges are like too much, right? So you can now get it together. So that's how we use log transformation. I hope that's clear.
Okay, so
So
there's another one again.
okay.
Okay, so there's another question again. So this is from Francis, right? He said that in practice, when building the model, at what point do you check for problem of autocorrelation, heteroscedasticity, and multicollinearity? To what extent do you rely on this prediction from the model in practice?
Okay. So using these features, right? Using feature selection process, feature creation process, and stuff like that. In practice, you have to. So one of the thing, as I said earlier, let me go back up when I was explaining feature engineering, is that it requires domain knowledge. Like it requires domain knowledge. So first and first, you have to understand the data you're working with. Understand what not to be there and what is to be there. What is useful for the specific output that you want. So a big time domain knowledge is important to understand your data set. So for example, now if I was doing as I said earlier, okay, so okay, yeah, now when I was doing feature selection, if the model gave me, for example, using when I was using Univera, and it gave me something like in the top 5, and it was giving me something like probably number of doors or something like that, that is important to you, the price of a car, but when compared to others, it's not important. Then I know that okay, something is wrong. When it's giving me year, it's giving me engine HP, it's giving me engine cylinder. A normal person, like we all know that these are important factors when you continue to get in a car, or when you be looking at the price range that a car would be, right? So having domain knowledge is important, and when the model now gives you these things, when you're trying feature selection processes and it gives you these things, then you now be able to like direct the model to to give you better features, and you have to create your own features within those things to to get it. But again, with domain knowledge, you still have to reach with this process to get better model. I hope I answered that.
To me, you answered it, but Francis, I hope you answered it. You can just say yes or something,
let me
but you
let,
can
let me
continue.
just move
You
on because of
can
time. Yeah,
continue.
please. Thank you very much. So log transformation. Then okay, the distribution again. Okay, the Gaussian distribution for the log transformation that we did. Let me move. That's that. So yeah, feature interaction. Another technique in feature creation technique. So feature interaction involves creating new features by combining two or more existing features together. So this technique can be particularly used when dealing with data that has complex interactions between these features. So complex interactions, it helps us to reduce the model work and trying to find patterns, because most of what we're doing in machine learning is just trying to look for patterns, looking for patterns within these features, and these patterns are complex. So trying to get insight from there. So helping feature interacting two or more features together that may have a complex interaction together, it can really help us. So for example, now so age, income, and location of a house might I think this doesn't say right. Yeah. So age, income, and location might be one very critical thing to consider when looking for I think house and so whatnot. So when you take the age, income, and location, you interact them together. Probably have a complex interaction. Then you might create a new feature with the combination of age, income, and location. And I said for our specific data set, features such as make and model, they can interact together, right? Because the make will make what make is it BMW, Toyota, what make is it? Then you have your the model that is Toyota Corolla, BMW, whatever it is. So you can interact those two features together, and Feature engineering such as the engine fuel type, the engine HP, engine cylinder can influence the performance and efficiency of the car, and they can also interact together. So I said it again, this is it's a very tricky part because it's tricky and it's an iterative process, and it is important to consider the impact on model performance and to avoid creating features that are highly correlated or redundant. So when creating this, you have to really look at if it's redundant, and it's really tricky process because you can most of the time create redundant process features if you don't understand your data set. But one very cool technique you can use is there's something called age statistics, right? Age statistics is used to determine feature strength. So, sorry, I'm just pausing my time here. So age statistics is something that indicates a strong interaction between variables. It suggests, okay, looking at two different features, it tends to like look at their interaction between them. Is it strong or is it weak? So if the interaction between the two variables is weak, merging them together might not provide much information. Like them interacting together might not provide much information. While if two variables, if their interaction using the statistics is high, then they can provide another and meaningful information within there. So I did a little competition for using age statistics here, and when you check that out, let me open this in the text editor. Okay, so looking at the make, looking at the relationship between the make and the model, you see that you have a 0.037, which is low. Here 0.01, and you look at let's look for a high one here. Okay, we have 0.07, 0.2. This is year and the year in PG. Can we get something better here? 0.7. This is quite high. So we see that the within the engine HP and the engine cylinder, the start is quite high. So going back to our to this, so we can see that the interaction between those two is quite high. So using age statistics, you can use it to measure the relationship between this feature and look at their strength and look at, okay, if these two features give me this higher strength, that means that if I combine them together, they can still be able to give me much feature. So I did a little feature interaction here. I created the Taiwo City MPG. That is using the Taiwo City DFMPZ and the Taiwo MPG with the City MPG. These are like two features that what I say. Okay, yeah, let's move on there. So engine HP and the engine cylinder is two much the engine HP, the engine cylinders, combine them together, you might get something new with respect to other features within your data set, and your make and model, something you can combine together as well. So this, be careful when doing feature interaction. You can create features that are redundant, and you can create features that are highly correlated with each other. So be careful when doing feature interaction, and I'll strongly suggest using age statistics when building feature interaction. You can read more about that. It tends to tell you the correlation between your feature and give you a sense of how they should interact with each other. So yeah, that's the three things I have for in the feature creation here for now. We talked about scaling your features, log transformation. We talked about feature interaction with each other, and yeah, we'll see more within this section. But as we move on, about I don't want to. Those ones that you can actually put them a whole topic on their own itself. So yeah, handling missing data, I would just roughly go towards this. So handling missing data is a common problem, and I'm sure we all as data scientists, machine learning engineer, we have seen data that we have dealt with data set that are missing before, and it depends on how do you solve them now? How do you impute those missing data is very crucial, because imputing missing data can make or break your model. That's something can make or break your model, because when you're okay, let's say for example, I've worked with a data set where more than 50% of it is missing. Karu commission data set, more than 50% of it is missing. Now, first, you have to understand the knowledge, right? Domain knowledge of this data set. What is it? How is it gotten? What is the what are the mechanism that which is the data might be missing? So understanding data, a missing data mechanism is very important when dealing with missing data. So the mechanism at which the missing data is important the missing data is missing. So is he just missing at random? Is it missing completely at random? Is it yeah, we'll get to that. So we can drop the data, as I said, drop the missing data point. It's easy to implement, can lead to loss of valuable information. Replace with constant values such as -1, 99, 999, etc. Yeah, you can do this as well, but it is best for when your data set is completely missing at random. That is completely missing at random. So we'll get to that mechanism when we get down. Um, Assigning medium, mean, and mode values. This you can also do this to your data set. You can use imputer to fill in the missing data. We did that above when we're doing before we trained our random first. We use a KNN imputer to input our data. Sure. Then we're using predictive methods as well to fill in missing data, where you try to use your data set to predict what will be within that particular area to predict particular missing part. So they can provide more accurate imputation compared to simple imputer like mean, and especially when there are complex relationships within your data. And the last one here is, there won't be any code here. This is just software I'm running through them. Last observation carried forward, our next observation carried backward. So this method is it's very interesting, and you can use this one for when you're having like your time series data, when the how will I say it now? The data is yeah, time series data or longitudinal data, when your data, when each data point is has a relationship with the previous data point, right? So I said this implementation involves carrying forward the last observed value and carrying it back towards the observed value in the missing value. So LOCF, which is the last observed value, observed carried forward, assumes that the most recent observation, that is the one at the top, is a good estimate of the missing value, while the NOCB assumes that the previous one is a substitute for the current missing value. So yeah, as I said, time series data, longitudinal data, what you're dealing with, the range as the way the data is in a time series format that is sequential, then this is, you can use it for this. And yeah, okay, yeah. Missing data mechanism is important. We just close with this on missing data. I said missing completely at random, which is, you have to understand the mechanism I was saying. When you have data set that is 50% of 50% missing, depending on how much how much data points you have. If you have like 1 million data points, okay, you have 500,000 to work with. It depends on you, depends on how you want to build your model. Then you say, okay, let me just drop it all. But dropping it all, as I said earlier, you're losing valuable information. So now you have to understand the mechanism at which this data is missing. So that's why sometimes when you're working with your own outsourced data set, then this might be, it's useful to understand this. But when you're working with competition, yeah, you might understand them as well, but you might not really gain much insight because they might not be in your domain of work experience, work expertise, or the data set might not be in your domain of work expertise. So missing completely at random, that is, in this mechanism, the missingness is unrelated to any observed and unobserved variables. So this one, you can say reward of is B, when you have a survey and the respondent accidentally skipped a certain question, or just due to one thing that is based on the observed variable and the unobserved variable, then yeah, it's just at random. It is something that you couldn't avoid, or you could have avoided, but it's not within the observed and the observer. So that is one thing the mechanism you should have to look at. Then missing at random again. So missing at random, when you say that, okay, how is this data missing? That is, it can be explained the observer, the observed variable, yeah, but not by the missing values themselves. So for example, if you let's say, okay, in a health study, if participants with higher income are more likely to receive to disclose their income. Yeah. So, but people with higher income, they might not want to disclose their income. Now, the missing of the income data is related to the observed variable, which is income, but not to the missing value, which is the health data itself, right? So, so it is important for us to understand this. And I said that it can be handled using technique like imputation based on the observed variable. So you can build like a model to like get the pattern and stuff like that within them. Simply imputer a can work within this because the observed variable can literally give you the data set can literally handle the observed variable. Yeah. Then I said missing not at random. Then missing not at random occurs when the missingness is related to the missing values themselves. So, for example, someone is not satisfied with their job. Now they don't want to, you ask them if they're satisfied with their job or not. They might want to disclose it because they know they are extremely dissatisfied and they're less likely to respond because they might also not be feeling it. In this case now, the meanness is related to the unobserved data. That is, they're not satisfied with it, and the missing mechanism is non ignorable there. So yeah, missing completely at random, missing at random, and missing not at random. You have to like put this all in context when you are building your model, when you're imputing missing data. You have to understand this and understand the mechanism at which your data is missing. Have I got any question? Hello?
Okay, yeah, there's some questions, but I think I'll make them speakers. But so why don't you just finish? So we just ask all the question at once.
Okay. How many minutes do I have left? Sorry. If I think I might have to jump.
No, you can still go extra. You can still go extra. It's fine. It's fine. It's fine.
Okay, okay. So handling outliers. Yeah, we know what outliers are, and yeah, they're in our data set, and sometimes they can occur due to a variety of reasons, such as measurement errors, data entry errors. But most of the times, outliers are usually, what outliers are, observed value that are just extreme, not within the range of the data set that we have. So one of the important things I noticed that I saw online is that that I see around is that people tend to treat outliers as missing value, right? So you treat outliers as missing value. You either just put them out, you either just pack them within your range of value, or just most of the time they just drop outliers, which I think is wrong because outliers are there. So instead of you, when you throw them out, and your model tends to see that in your model sees that as an input variable when during production or something like that. It tends to like, okay, not understand what's going on or something like that, and give you the prediction that is not worth it. So we have to understand that outliers are part of our data set, and instead of just pushing them out or cutting them off, how do we deal with it? How do we land those outliers? So I would say it's not appropriate for you to delete your outlier data set, outlier points, because they are part of your data set. So first and first, when dealing with outliers, is that you have to visualize the outliers and then look at your outliers and what is it, what is there, if outliers is there or not. Okay, yeah, I think I'm just looking if I missed anything. Yeah, so visualizing outliers. I said visualizing statistical model. So visualizing outliers, you can use your box plots, scatter plots, and histograms. And statistical method, you can use this called IQR, interquartile range, and you can use Toki's method as well. So for explanation here, I'll be using the interquartile range here to show us how to detect outliers first. We first look able to visualize and detect our outliers. So we're using our popularity variable, popularity feature here, because it is one of the the very skewed out of range data that we have. Because when you are looking at the max trend data popularity, and when you're looking at the maximum, I have 5,657, and you have your mean. Yeah, so this might not necessarily mean this it's an outlier because you have to look at it related to your data set, but you have to look at related to your other variables and you have to visualize that. I'm just using that because it has the highest range of value within the whole features that we have. So there's a formula for using interquarter IQL to detect your outliers. So the way it is done is that you have outliers, right? Then you to detect it, then you take the 25 or let's say you take the Q1 and the Q3. Now the 25% and the 75% of the data set that your data set respectively. So you take the 25th percentile and the 75th percentile and you put them within a range, right? So when you get the range, it is within that range that you now see that, okay, I have this lower limit and I have this upper limit. Whatever data is out of this lower limit, it is an outlier. Whatever data is out of this upper limit is an outlier. So using IQR to calculate it, you first yeah, so this is a formula right here. I'm sorry, it's kind of messy. I didn't so the data points which fall below Q1 minus 1.5 IQL or above Q3 or 1.5 IQL are outliers. So now you have to know, okay, what is your data? Is your data a normal distribution, a Gaussian normal distribution, or a skewed distribution, right? So the formulas differ. Looking from above, our data is positively skewed. Yeah, I think that's when we are. Sorry. Well, yeah, where's this? Where's this? Where's this? Okay, okay. Yeah, our data is positively skewed when you check the using the DF imputer. Yeah, it possibly skewed a little. So we can then use the skewed formula. But if it was a normal distribution where you have your mean, which is your mean is 0 and your standard deviation is 1, if you scale it using min max, I think min max should be able to do that. Min max scaler can give you a normal distribution or something like that. Then you can use your this formula, right? So any data points that fall within mean minus 3 times the standard deviation ST or above mean plus 3 times standard deviations are outliers. So these are those formulas that we use to detect them. So at first you find your first quartile and your third quartile, then the interquartile range is here. Then you using the formula that we put here your Q1, which is your first quartile minus 1.5 times your IQR, which is the range, interquartile range that we've calculated up above. Then that is for your lower limits. Then for your upper limits, you get your Q3 plus 1.5 times your IQR. So that gives us the upper limit of 499. Then you have a lower limit of 169. So any of these points out of this, we can classify them as outliers. So doing a simple check, we check if there are any data points outside our limits, our upper limits and lower limits, and running with that. Okay, running with that. So we have true, we have data points there. So let's see what they are. We have about 888 rules and out of 11,641 data points. So visualizing them can like visualize them and see that, okay, this is your Q1, your be able to visualize. Now how do we deal with this now? Now the thing is, you can deal with them using capping and flooring method, or you can deal with them using winterization. That please when it's 10 minutes before the time is off, please just notify me so I can quickly round up.
It's
All right,
actually 5 minutes.
5 minutes. Okay, okay,
Yeah.
thank you very much. Thank you. I'll round up now. I'll round up now. So yeah, you can remove outliers with capping and flooring method. I'll just explain the way that works and you can check out the code. The notebook is on key up there. So capping and flooring is involved setting a maximum and minimum value. Then, as I said, anyone that is outside that, it is removed. Simple thing I was did here. Anyone that is outside these values, or here and here, we do what we remove them. It has given us a range of our data set to be able to understand that, okay, this data point within this range and this range are good to go. So I did some simple thing there, and we got our outlier. Now we can see that we can now see that the range is now 4,000 to 0. But the thing is that it's range now 4,000 to 0, but the distribution of the data set has changed, right? So yeah, before going to miniaturization, that's what I want us to know, that the distribution of the data set has changed. So as the distribution has changed, we have reduced the data, we've removed some of them. As the distribution have changed, this set is now a new, and it's now trying to detect, okay, is there a new outlier in this, is there a new outlier in that? And that's why we are seeing this again. Look at the range here, we have 0 to 4,000, and look at that, we have 0 to about 6,000. So it has removed them, right, using our upper limit and lower limit, but it's still like trying to tell us again that we can still do more, which we actually don't want to do. So that's why when serialization comes in, right, instead of replacing those extremes values, instead of removing those extreme values, right, we replace them with the top 1% of the values, right, with the 99%, top 1% is replaced by the 99%. So virtualization is really robust, and it preserves your data distribution, and it's simple. There are some disadvantages as well. Information loss, you have your impact on statistical analysis. I think, yeah, let me just show what it is here. So when you use visualization, is you can use it on SciPy. Now, what I did here is I trimmed the 10% at both end. So at both end of the upper and the lower bound, I trimmed the 10% of those data and visualized them. So still quite the same, but now that extend the old data set out to distribution that is more favored with the with respect to the old data set. So yeah, I would advise visualization when dealing with outliers. You can first of all check if the outliers, check how many do you have with respect to this set, and deal with it as just needed. Finally, dimensionality reduction. It's a big technique. It's more than I've talked about here. You have to read on it if you want to really go in deeper into it. And yeah, talked about reducing the features. So the main crux, the crux of dimensionality reduction is just that you have millions, hundreds of thousands of features, right? What we want is that we want to reduce these features. We don't want to lose the information within them. We want to reduce its size as well, and we want the data points to reflect the same feature as if we are using the main data set, right? As if we're using the original data set. We want to capture the underlying data distribution within them, underlying data patterns, we want it to capture. So we're using dimensionality reduction to use it. Cost of dimensionality, sorry, we can't deal with that right now. So you can check that out. But yeah, you can read more on this. I think I put something a lot on this. And yeah, so first and first, when you're dealing with dimensionality reduction, is you find your number of components. And your number of components are derived by the features which can explain the maximum variance in your data. The number of components, once again, are features that determine the maximum variance in your data. So you calculate the number of experience variance ratio, and from here now we can see that my variance is 1, is 14, variance at 12, at let's say 0.9. So yeah, so that's it on principal component analysis. And when I use 9 components here, I got a new set of features, right? A new set of features from the one that I have earlier. So please, if you're interested in PCA, there are two very common methods using dimensionality reduction. That's PCA and TISNI. TISNI is more of using data visualization to visualize within the capture the relationship within data. So you can use it for when you have very, very, very large data set. So yeah, so read more on PCA and TISNI if you're interested in this, and advice too. So yeah, I think that's all for now. Thank you very much. If I have any questions, please go ahead. Sorry.
Okay. Awesome, awesome, awesome. So Francis, I've made you a speaker because he said you were unable to answer his question. You answered one part out of two. So Francis, can you unmute yourself if you stay there? Hello, Francis. Hi, Francis.
Hello?
Yeah, we can hear you. We can hear you.
Yeah, good afternoon, everyone. Yeah, thank you very much. for the presentation. So, my question was the first part that has to do with, because before building all these models, right, there are certain things, assumptions that you must check before you can even rely on that predictions, right? So there are certain assumptions such as problem of multi-collinearity, autocorrelation, and heteroscedasticity. So my question is, how do you take care of these things? Because most time when I see it, it seems that they just build the models, but I don't see how they take care of these problems. Because once any of these problems is there, you cannot rely on those results or whatever outcomes you have there. But I see
Yeah.
most time, most people just assume that the result is okay and they do not test for these things because they are very fundamental before you rely on that result. So that's the question. How do you take care of these problems in practice before you start building your or deploying it?
Okay, yes. So one thing is that I think you said assumption, right? So um there's no assumption, right? So when you get your data set, right, the first thing you do is do some analysis, check your missing data. If you have any missing data, look at your variables, categorical, look at their cardinality, how are they doing? Then you check those stuff, right? So when you look at all those things, then you now see, okay, you check your correlation as we did here. Sorry, you check your correlation, look at features that are highly correlated. Like this is when I did under the feature selection, right? um look at this correlation metrics now. From your correlation metrics, it's able to give you an understanding of features that are highly correlated and features that are not highly correlated. So as I was saying that, from there you get an understanding of, okay, what my data is, what is in this data point. You see engine cylinders 0.7 with engine HP, they're they are very correlated, right? So from there you understand what your data is. So feature engineering is just understanding the data set, trying to build something, trying to create new things from the data that you have, trying to remove those ones that are relevant. Now, do you know those ones that are relevant? Looking at the feature importance. How important is this feature? Looking at the correlation within each features, looking at doing statistical analysis of these features, and trying to get the point of your audit set. So this is like part of your data, the data analysis process, your feature engineering process. And before building your model, you have to do this. So when you now finish building the model, right, you build V1, right? When you finish building V1, because this is building model is not just something you do once and you say you build V1 and you're done. You do it's an iterative process. You can use CV, cross validation. So when you use cross validation to test, okay, the data pipeline, you build data pipeline using SQL, different pipelines, different feature engineering processes to do those things. Then from there, you look at, okay, is my model overfitting or underfitting? When you finish doing processes, look at different model. You build 5, 6, 7 models. When you see this data set, they have built like 5, 6, 7 models to be able to get to achieve what they did. Sometimes you can use assembly methods and things like that. But when it comes to those things, it's not just one model you build. It's an iterative process, as I said. I hope that. I hope that.
Okay.
I hope that.
I think you were actually clear, very clear. But Francis, hope that was okay for you. So can I have other
I
questions?
get where you're coming from, but you see, so what you're explaining with the correlation actually is actually checking for the multicollinearity, right?
Yeah, not
Because
just correlation that you that
so
you
hold
that
on,
you,
come here. I'm just trying to explain something. So what you're trying to check with that correlation matrix actually is also a way of checking for the problem of multicollinearity, where the variables are highly correlated. But however, even where they are highly correlated, and because we are trying to predict, right? So sometimes multicollinearity may be a problem we can embrace, right? But you
yes,
see,
that's where domain knowledge comes in now.
uh-huh. Yeah, that
Because
way, I think second part, that's where you explain that domain knowledge will determine what is relevant for you and how reliable
yeah,
it's going
so
to
I'm
be.
saying that domain knowledge will help you shape the understanding of what the model is giving you, right? Will help you shape the understanding of the different processes that you're going to use in this to get your model out.
All
Okay,
right, thank you.
okay,
Yeah,
okay.
thanks.
So what I can do is I can link Francis with Samuel. I will send Francis Samuel's LinkedIn. Samuel, can I send him your LinkedIn so you guys can
Yeah, sure.
like discuss
All right,
more
that's fine.
about
Thank you.
that
Thank you.
like I think you guys have a lot of ideas to like Oh God, you data guys are so amazing. Okay, so Samuel, the last two question was, which I asked you already, was you're going to tell us how you started your old data journey and also what advice you have for people just starting out in the data field. So over to you.
Yeah, starting the journey was in university. I think that I should know about this as well. When DNS, this Science Nigeria, where we started at FUTA. So that was where the journey started, and yeah, that's where it's been. That's how it's been going to now. Right now, I'm currently machine learning engineer at DEMS. So what I just do is build machine learning models, and deploy them. So and that's most of it. So the journey is just from school, FUTA down to NYC, then start doing all these things. So it's not. I don't know if I should say more on that, or I don't know. Okay. And the second question is
What advice?
okay. Okay. I'm also looking at advice for myself. So I'm still young in this. I'm relatively young in this, and yeah, but it's just the grind. I think one thing I can say is that just pick one or two domains to literally focus on and grind on that. If you're going to data analysis, data engineering, and if it's machine learning, you can just go into machine learning, computer vision, NLP, recommender system. Yeah, it's better to just yeah, know all these things widely, of course, but have an expert in some particular place that people recognize you from. I think that's what I can say.
Okay, awesome, 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 awesome. So I'll stop the recording. So for everyone, the recording for this session we made available